This is lecture 21, and in lecture 21 we're going to talk about boosting. And boosting is in some ways typically taught alongside bagging, and we'll talk about its relationship and not for boosting related to bagging or advanced bagging techniques like random forests. So before we talk about boosting, one of the kind of central topics in boosting is going to be about loss functions. In order to understand some of the kind of commonly used algorithms here, we have to talk a little bit more generally about loss functions. So this is something that we've talked a little bit about, but we've only really worked with two loss functions so far. So for the regression case, we particularly worked with what's called the squared loss, or the squared error loss, where my loss for some function f is y minus f of x quantity squared. All right, so this is the typical loss we use for regression. And another loss that we kind of briefly mentioned would be the absolute loss. And this would define L of f to be the absolute value of y minus f of x. Now, there are some real nice theoretical properties of the squared error loss. In particular, this thing can be written as an inner product, or at least this kind of sample version of this can be written as an inner product. It's going to be differentiable, generally speaking, because say the square or something, whatever squared is a differentiable function. However, it's not going to be particularly robust. And the reason it's not particularly robust is because it has the square term. So it's going to put more weight on errors that are large than errors that are small. So this is kind of akin to something like a variance, which is going to kind of look at a squared error. It's not just the error, but it's the square of the error. Alternatively, the absolute loss is not differentiable for all possible values. It can't be written as any kind of nice inner product, but it is more robust. And so in realistic situations, when you have outliers or your data doesn't really exactly follow your model, it's not going to be overly influenced by large errors. So if we think about, both of these can be written in terms of what we might call R, which is the residual here. So here R is just y minus f of x. And the sample version of these would be the average over our training data, yi and xi, or yn and xn, right? And what we can see is that the squared loss squares the residuals, whereas the absolute loss takes the absolute value of the residuals. So if I'm optimizing my function, f, and I have a large residual, the squared loss is going to pay a lot of attention to making sure that that large residual is minimized as much as possible by my choice of f, because it squares the residual. Whereas the absolute loss, it's not going to pay as much attention to that large residual. At least it's going to kind of scale. It's not going to scale in a squared way. So these are kind of two common losses for regression. And for classification, and I'll just note that both the losses for regression can basically be written in terms of this residual. For classification, and particular we're going to focus here on binary classification. You can extend some of this conversation to more general classification setting, but let's just start with binary. That's the easiest place to start. We basically have two ways of parameterizing a binary classification problem. So the typical scenario we've worked with so far is that my response variable y in the binary classification is one of two classes. And so one typical way of parameterizing that is y is in 0 or 1. Y is 0 or y is 1. Just two classes. But those numeric labels are kind of arbitrary. And it is often more kind of, let's say, theoretically useful to think about parameterizing our two classes as -1 and 1. So we've seen this before in some of the homework problems. Again, the labels are arbitrary, but this second parameterization just often makes the math easier. And you saw that in our problem set 3. You could see in that first problem that this made the math really slick. Now you can transform back and forth between these parameterizations as a one-to-one function. If I want to go from a 0, 1 encoding to a -1, 1, I can just look at, if I multiply y by 2 and subtract off 1, that will map 0. 2 by 0 minus 1 will be -1, and 1 by 2 minus 1 will be 1. So that will map us that way. And if I wanted to go in the opposite direction and go from a -1, 1 encoding to a 0, 1 encoding, I could just do the inverse function, which is y plus 1 over 2. So that would map -1 would be -1 plus 1 is 0, over 2 is 0, and that would be 0, and 1 would map to 1 plus 1 is 2, over 2 is 1. So that you can transform back and forth between them. They're identical. It's just sometimes more useful to think about y as taking on -1 and 1 instead of 0 and 1. And we'll see why in this discussion. So we want to talk about losses for classification here, right? And the first kind of primary loss we worked with was our 0, 1 loss. And this is actually the only one we've seen so far or explicitly seen so far for regression. And this said that L of f was just an indicator that y is not equal to f of x, right? So this is 0 if y is f of x. We have no penalty, no loss if our predicted class f of x is equal to the actual class y. And we have one single unit of loss if y is not correctly predicted by fx. Now, what we can notice about this, so this is what we can notice about our second encoding here. So let's think about our second encoding here. Is that in our second encoding, if the signs, so let's say aside here. So here we're going to work with our second encoding. Y is in -1, it's either -1 or 1. And f of x is also predicting in this class. So f of x is either -1 or 1, right? Because it's predicting one of these two classes. And what we notice is that if the signs of y and f match, y and f of x match, we've done things correctly. So if signs match, that is, either y is -1 and f is -1, that's correct. That's a correct classification. Or if y is 1 and f of x is 1, that's also a correct classification. If our signs don't match, this is an incorrect classification. And so we could actually write in this second version, or a second encoding of y, we'd actually write our loss function here in terms of the kind of signs of y and f. We actually don't care about the values. I mean, I can make it, instead of negative 1, 1, I can make it negative 10 and 10. It doesn't really matter. The numeric value is not telling us anything. It's just whether or not it's positive or negative. So more generally, for any possible classifier f, there is some function h so that f of x is just the sine of h of x. And so this is often how you will see, when you encode with this negative 1, 1 encoding, this is often how you will see a classifier written, as the classifier is the sine of some function. So this function f has to output negative 1 or 1, but of course it will. The sine function outputs either negative 1 if it's a negative number, positive 1 if it's a positive number, or 0 if it's in between. So let me just write that out. Sine of some value y, oh, let's not use value y, let's say a is 1 if a is bigger than 0, negative 1 if a is less than 0, and 0 if a is 0. So that's a classic sine function. So ultimately, this f outputs just negative 1 or 1. I mean, you can ignore the 0 case. And since that f outputs just either negative 1 or 1, you can always write it as the sine function, which outputs negative 1 or 1, basically, of some other real valued function h. And so you'll often see classifiers written in this form in, say, computer science or statistics literature as just the sine of something. But that's all that's happening, is they're using this negative 1, 1 encoding. And we can look at what is called the margin. So the margin for a classifier is y, not times f of x, but times h of x. So the idea with this h is that it's a real valued function. H is much bigger, or let's say h of x is big if, hopefully if y is 1, and h of x is going to be really negative if y is negative 1, right? And so h is kind of like a discriminant function in some ways. It's going to tell us the bigger h is, the more positive h is, the more kind of evidence we have that it should be class 1, and the sign, of course, will be 1. If h of x is really, really negative, this is more evidence that we have a negative 1 class, and of course the sign of that is negative 1, right? So while f of x just tells us 1 or negative 1, doesn't give us kind of a strength there, h of x tells us the strength of it. And so we can look at what's called the margin, and the margin of a classifier, written as this parameterization, is y times h of x. And notice here that this thing is bigger than 0, that is, the signs match, if we have a correct classification, right? So if y is negative 1 and h of x is negative, this thing will be positive. If y is 1 and h is positive, this whole thing will be positive, correct classification. If it's less than 0, this is an incorrect classification. And more to the point is that, like, the absolute value of h of x, the size of h of x, is the incorrect or correct amount. So if it's really, really positive, that means we have big confidence that we have a positive 1 class, a plus 1 class, and it is plus 1 class. If it's really, really negative, either we're really confident it's a class 1, but it's actually class negative 1, or we're really confident it's class negative 1, but it's actually class 1. So this margin tells us kind of the incorrect or correct amount. And So this margin is similar to a residual in the regression case. Right, so in the regression case, we have this residual, and all of our loss functions are written in terms of this residual r. If r is big, we did things wrong, kind of in magnitude. If r is small in magnitude, we did things well. And you can write your loss functions in terms of this residual. For classification, it's kind of theoretically nice to work with this -1, 1 parameterization, because we can define this thing called the margin, which is just really simple y times h, because any classifier you can write as the sign of some function h. You can define this thing the margin. The margin plays the same thing as the residual. But now is the margin really positive? That's great. Or really negative? Ooh, we're not doing well there. And we can write the loss functions as a function of our margin. So in the same way in the regression case, you can write this as a function of the residuals. You know, we can write our 0, 1 loss, let's say 0, 1 loss, L of f as this is going to be the indicator that our margin is negative, right? So let's step back and understand why that's true. If YH is negative, we made an error. And so our loss gives us a unit of error, a unit of loss, if we made an error. And so this is the same thing as saying the indicator that f is not equal to y, right? Because y of h, the margin, being negative means we've made that error. F of x is not y, because the signs don't match. So this is, for example, the 0, 1 loss. And this whole thing kind of unifies our theory because it's now written in terms of math, right? It's written in terms of the product being less than 0. Which is kind of easier to mathematically deal with rather than discrete categories, right? So this is a kind of unifying theory of losses across classification and regression. We can draw a picture of this. So we can, on our x-axis, we can draw our margin. And we have 0 in the middle. 0 is basically the decision boundary when our margin is 0. Let's just call it YH, that's the decision boundary. And our 0, 1 loss gives us a unit of loss if it's negative, and then as soon as the margin becomes positive, it drops down to 0 units of loss. So that's, if we plot L of f, our loss, against the margin, that's what the 0, 1 loss looks like. But this is not the only loss we could use. Any kind of thing that behaves similarly penalizes negative values of the margin and less penalizes positive values of the margin also works. And you can come up with lots of these, and people have. One that's particularly important is called the exponential loss, and it's going to look, let's see if I can draw this correctly. It's going to look something like this. This thing is called the exponential loss. And its formula, instead of the indicator, so here our 0, 1 loss, the formula is the indicator that our margin is negative. Here, the exponential loss has a formula of e to the negative times our margin. So that gives that blue line that we show. And so notice, it's continuous, it's differentiable, so it has some nice properties that the 0, 1 loss doesn't have. So it's kind of one of the natural losses out there for classification. And we notice that if we have negative values, we get a higher loss penalization. If we have positive values, and as the margin becomes more and more and more positive, we penalize things less. Now, we don't penalize 0 for a correctly classified thing. We penalize less if it's more correctly classified, our margin is larger, and less if it's less correctly classified. That is either closer to 0 or indeed it's negative. There are lots of other losses out there. The last thing I'll note is that you could also look at, so let me just write that down as a second important loss, which is called the exponential loss. And that has the formula exponent of negative y times h of x. And h will be kind of implicitly defined by your classifier. You could also instead use the squared error loss, right? So if you looked at a squared, if you just looked at this, it's supposed to hit 0 here. Let's pretend I hit 0, right? Why couldn't I just look at, say, the margin squared, right? Can't I use a squared, like, you could think about doing this, right? Why don't we use a squared error loss for classification? And it would look something like this. So it's doing okay. It penalizes negative values of the margin. Cool. And it's going to penalize these first bit of these positive values of the margin less. But then it starts to penalize the large values of the margin a lot. Now that doesn't make any sense to do, because these are correctly classified. So if I have a thing with a huge margin, kind of really strongly correctly classified it, why am I forcing my classifier to focus on that? We don't need to focus on that. So the fact that this is not monotonically decreasing, which is really what we want of a loss, is not a great property of the squared loss. So this is kind of basically the reason why you don't use a squared loss. Because you could. I mean, if you have a 1 and a negative 1, you could literally take your difference and square it. But this is what the loss would look like in terms of the margin, and it doesn't make as much sense. So that's why we tend not to use it. So the 0, 1 loss is kind of the classic loss. Something like this exponential loss is what's called a surrogate loss. It's kind of a surrogate. It's a nicer version that approximates the 0, 1 loss, but isn't quite the same thing. But it's going to have some potentially nicer properties to it. It's differentiable. Okay. So that is a tirade on losses. And I think that nicely ties together some of the discussion that we've had so far with regression and classification, different losses. So just as a real quick aside, right, we did regression with a squared error loss. You could do regression with an absolute value loss. That is called quantile regression, or generally, if you look at the quantiles, it's called quantile regression. In particular, absolute value would be the median regression. It's a more robust version of regression. You could do classification with a 0, 1 loss, and you can also do it with what's called this exponential loss. And you can do, there's other ones called like deviance loss, and you can somehow interpret, say, logistic regression as using a particular loss. So we kind of de-emphasize that, but you could interpret logistic regression in that way. And so in some ways, the difference between like LDA and logistic regression and, say, just fitting a linear model to negative 1s and 1s is the loss they're minimizing. Okay. So in particular, we're going to talk about a class of methods called boosted methods. And this is typically taught alongside bagging and random forest because it's some kind of ensemble method. So it's originally motivated as an ensemble method. Or a consensus. That's nice. So consensus method. And the idea there is, can we combine a series of weak classifiers, let's just say weak methods, because you can do it for regression or classification. It was originally motivated with classification. We'll talk about that, but you can do it for regression too. But generally, can you combine a series of weak methods to form a stronger one? So this, in some ways, seems similar to a random forest, a bagging method, where you have a bunch of trees, which are okay, but they have their issues. But if you combine them, you get something better than the individual. So this is typically how it's taught. There's bagging and there's boosting. It's not necessarily the way statisticians tend to like to think about these things. And so this is a traditional way of thinking about it and how it was originally motivated. But we'll talk about a better way of understanding it in terms of loss functions and in terms of these kind of adaptive methods. So we'll see. But at the end of the day, it's probably not the best way to interpret what boosting is actually doing. So we're going to talk about the original motivation. And in this original motivation, we have a weak classifier. And a weak classifier, so we're going to talk about in classification setting. So let me just write that. What we're going to say here, you can generalize your regression setting, you change the loss. It's basically all you have to do. There's a discussion there, but we're first talking about in classification setting. A weak classifier is basically a classifier that is slightly better than random guessing. And in particular, we're going to talk about this in the binary classification setting. There are generalizations that are a little beyond the scope of this lecture about this approach to non-binary things. So a weak classifier is just something slightly better. So if we have two classes in the binary setting, something that 51% of the time gets it right. Not a great classifier, but slightly better than random guessing. And boosting is a method that is basically going to follow two steps. It's going to sequentially apply weak classifier, or let's say, and let's not say apply, but learn weak classifiers. It's not how you spell weak classifiers to a series of modified training data. So what we're going to do is we're going to build a series of classifiers. F1, F2 hat, F3 hat, F4 hat, ... right? We're going to build this, and what we're going to do is we're going to build the sequence of classifiers and every time we build a new one in each iteration, we're going to fit it to a slightly modified version of the data set. And then our final boosted classifier is going to be basically a ensemble or a weighted version of the original classifier. So I'm going to sum I goes 1 to, let's say we have M classifiers. We could say, let's say B. Let's say B for boosted, sure. And so we're going to have, and we're going to fit our final classifiers basically. Our final boosted classifier is basically going to be a weighted vote of the original, of the sequence, the series of classifiers. So here, this thing is basically a weighted vote. Notice that when I write this in a -1,1 parameterization, I can, of course, write my classifier as the sign of something. And if I write this as the sum, a weighted vote is basically the sum of ones and negative ones, right? So if I sum up a bunch of ones and negative ones, it's either going to be end up with a negative number if I have more negative ones, or positive number of more positive ones. And if I take the sign, that will tell me the relative proportion. I have more ones, that means I have a positive sign. That means I predict class 1. That would be basically the majority of things vote class 1. Or if I have more negative ones, then I'm going to get a negative number. My sign will negative. I'll predict -1. And that's the same thing saying I take a weighted vote of each of the classifiers. And my weights here are these alpha. See, these are my weights. And my weights are going to be higher for a good classifier and lower for a bad classifier. So on the way, I'm going to learn these weights, which of these Fs do well and which of them do poorly. And my final vote is basically a weighted vote of these things. And what I'm going to do when I modify these is I'm going to, at each iteration, I'm going to modify them to focus training on examples that were misclassified in previous iteration. So basically what I'm going to do is I'm going to start with some initial classifier, and I'm going to classify things. And I'm going to look, where does that thing do well and where does it not? I'm going to reweight my training data. In the next iteration, I'm going to fit another method, a second one, but I'm going to fit it in a weighted way so it pays attention to the places where the previous one did poorly, and so it forces that second one to focus on the parts where it did poorly and learn those examples. And then on the third one, I'm going to look at where the previous one, where that did poorly, and I'm going to focus on those, and et cetera, et cetera, et cetera. So I'm basically fitting in a weighted way, not only in each iteration, but then my final weighted vote, my final classifier, is going to be weighted based on the accuracy of those constituent classifiers. So that is the one way of motivating what the boosting algorithm is. And this is the original way that it was motivated. And it gave us an algorithm called Adaboost, presumably named after Ada. Maybe it's adaptive. I don't know. Ada Lovelace, right, was one of the first computer scientists. She was the daughter of Lord Byron. Interesting historical character. So my guess is that's a pun on her name. There's a lot of things named Ada in computer science, and this was, I think, developed by some CS guys and gals. So here's the Adaboost algorithm. Step 1 is I'm going to set weights for each training example xn, yn. So I'm going to set a weight for my training examples. And initially, I'm going to set them all just to be 1 over n, number of things. That's the kind of initialization step. And then I'm going to build my sequence of classifiers. So let's say for B, which is my classifier index, my boosted index, from 1 to capital B, substep A here is I'm going to fit some classifier f hat B on training data, let's say on weighted training data, weighted by the WNs. Basically what this means is that I'm going to fit a weighted loss. So for example, if we fit a tree, I'm not going to minimize the RSS. I would minimize the weighted RSS. Or for classification, instead of minimizing the misclassification error, minimize a weighted misclassification error when I fit this. I'm then going to, in step B, compute the error for this classifier FB hat. So E for step B is going to be my weighted, let's say, just say weighted misclassification error. This will allow me to calculate my weights. So for our final classifier, we're taking a weighted sum. We have these alphas, which are our weights. And those alphas are going to be for the bth classifier is going to be basically log of 1 minus EB over EB. So what this looks like is my misclassification error can be between 0 and 1. Or let's say my accuracy of that can be 0, 1, and this is basically what's called a logistic function that looks something like that. So if I'm going to have a high weight, so this is my alpha is my y-axis, I'm going to have a high weight if my accuracy is close to 1, and a low weight or negative weight if it's close to 0. And then I'm going to reweight training examples, my training data. So originally I start off with the weights of my training data all being equal. I fit a classifier. I compute the error for that classifier. I compute this alpha, which is going to be the final weight in my boosted classifier. And I'm going to reweight my training examples based on did I do it correctly or did I do it incorrectly on this iteration. So Wn is going to be updated. So here's my kind of arrow for updated to. And it's going to be just stay the same as Wn if I classified correctly, or Wn is going to be updated to e to the alpha b times Wn if I classified incorrect on that iteration. So basically what we're going to do is if we classified correctly, we're not going to change the weights. If I classified incorrectly, I'm going to up the weight on that example for the next iteration. So my next classifier, as I go back up to the top of this loop, is going to be fit to focus on the example I got wrong. And so my next classifier is going to fit to the weight training data. It's going to focus on the ones I got wrong last time. It's going to compute the error. It's going to compute that weight. And then at the end, so this is all kind of step 2, at the end, of course, step 3 is just that I output my boosted classifier, or my Adaboost classifier, which is just the weighted sum of this series of classifiers. So that's the basic boosting algorithm. It was the first boosting algorithm come up which was named Adaboost. It was developed in the mid-90s, I think, by a series of computer scientists, and I think it has a nice motivation, which is basically we're iteratively building more and more classifiers to focus on the examples where we get things wrong, and then we're taking a weighted average or a weighted vote of the classifiers at the end based on how accurate they are. If they're more accurate, they get more of a vote. If they're less accurate, they get less of a vote. Okay. So that was a nice, fun, and easy motivation for the lecture. The question is, what is boosting doing? Let's say really doing. Or maybe the question would be, why does it work? So, and let me back off here and say that typically, that this FB, right, is supposed to be a weak learner, a weak method. And so typically it is a stump, what's called a stump, which is a one-split classification tree. All right, it's a tree with exactly one split in it. It's called a stump, kind of joke. But that's a really weak method, right? I just literally pick one covariate and I split on it, all right? And so that's very much a weak learner. And you'd think those would do bad, but if you actually do this and you average them together, it actually does quite well. And these are one of the more powerful methods, kind of modern methods out there. So the question is basically, why does this work? And at the end of the day, the boosted method it can be thought of as an additive an additive model or an additive method where f hat of x is, what do we say, it's the sine of the sum, it's basically the weighted vote, but we can write this the sine of the sum of the fb hats, right? And maybe I could call this thing in here h of x, right? So here h of x, which is really the crux of the algorithm, is this additive method. It's a sum of a bunch of fb's. Whoops, and I'm missing my alpha. Weighted individual methods, right? So the individual methods are all of some class. Typically, they're just stumps. They're one-split trees. And we could generalize the generalized additive method. The generalized additive method would be h of x is some weighted sum of, let's say, alphas times some, what do we want to call it? Let's call them beta of x. And let's say beta of x, and beta is going to be parameterized by some set of parameters, gamma. Okay, so these betas are basically a set of basis functions. The gammas are whatever the parameters for our basis functions. So for polynomials, the gammas would be like the coefficients. For trees, the betas could be trees. In that case, typically they are. The betas are these trees, and the parameters are like the splits and the values that are predicted at the leaf nodes, for example. But you could fit any kind of class of functions, call it beta, that are parameterized by some set of parameters, gamma. So the beta is parameterized by gamma is some class of functions. And in particular, maybe we pick the betas as some trees or as some polynomials or whatever. But this is what's called kind of an additive model, where we're modeling, in this case, h by some additive, some addition of some weighted basis functions. So this is like a Taylor series is a way to think about it. And so there are many, many types of additive methods out there. And sometimes regressions are really simple, or like polynomial regression would be a really simple additive method where our betas would be like polynomials, and the gammas would be coefficients. You could actually look at trees as some kind of additive method, and we kind of wrote them that way, where the betas are like the rectangles, or kind of related to rectangles, etc. Right? So ideally, with an additive method, we would we'd find h by minimizing over all of my alphas and all over my gammas. I guess the gamma should be indexed for each. It can be a different gamma potentially for each beta. So ideally, we minimize over our alphas, and we minimize over our gammas, and we minimize some loss that measures difference between whatever the true h's are, for example, and the function we predict. So it basically would be minimizing a loss of this thing, right? So let's write this. So this is my notation that say it's a function of x and it has its parameter, right? Now for classification, this loss would be something like a 0, 1 loss, or an exponential loss. For regression, this would be something like a squared error loss or an absolute value loss, right? But you have some loss function that tells you how well this particular choice of gammas and this choice of alphas work. And here L is my loss function, right? So it's kind of classic thing. Basically, you see polynomial regression as an example. This is a complicated problem to solve. because basically there's a whole bunch of these parameters that you need to optimize over, right? In the general sense. You can view a boosted method. A boosted method basically adds these on one at a time. It builds one, then adds on another, then adds on another, then adds on another, right? It builds up a series of these. And so you can view a boosted method as solving a similar kind of problem in what's called Stagewise additive modeling. And Stagewise additive modeling is basically going to say only optimize one parameter, or one parameter, let's say, at a time. Or only optimize over 1b at a time. You're only going to optimize over an alpha and a gamma. And then we're going to go on to the next one. And so basically what the algorithm does is, for b goes 1 to b, we're going to approximate a solution to this by, at each point, we're going to get an alpha and a gamma that are the arguments that minimize over all possible alpha and gamma. What we're going to sum, we're going to basically look at so if we do this over a training data, say summing over a training data, instead of over everything, we're just going to add on, right? So an additive model is a sum of these bunches of these things. We're just going to add one at a time. First, we're going to start with alpha 1, gamma 1. Then we're going to add on alpha 2 and gamma 2. And we're going to build up this model one stage at a time. So this is called Stagewise additive modeling. So it's a little bit cumbersome to write. Let me just write it out, and then I'll kind of explain the notation. Okay, so we're going to start with some initial model, and then what we're going to do is at the bth iteration, at iteration b, we're going to take the previous model. So we start off with none, and the first step is we just find the first best approximation. Once we have that, we have like f1, we're going to look at we're going to add on a term. So we're going to add on one of these terms at a time, right? So you see this term here, which I guess this alpha depends on our b, right? It is one of my terms from this sum. So we're basically going to build up this sum one thing at a time. It's not globally the optimum thing to do, but we're going to fix the previous terms and add on one at a time and just optimize as we go. And so we're going to look at the loss of the previous stage, plus if I add on another term, and I'm going to optimize my alpha and my whatever parameters for this thing just locally for that one step. So it's basically a greedy approach, and then I will update. So at iteration b, it's just going to be the partial solution from the last time. I'm going to add on my optimum solution, something like this. So the math is a little bit cumbersome, unfortunately, for boosting, which is why it's often not talked about in these kind of courses, because it's kind of cumbersome. But the basic idea is that you can view a boosted method as fitting some kind of additive model. And it's fitting the additive model, if you go back up to our Adaboost, is it's doing it iteratively, where it's fitting, then it's reweighting, and then it's fitting, and then it's reweighting, and it's fitting, and it's reweighting. And so it's building up this sum here, one at a time, based on the answer to the previous. And that's what we call additive stagewise modeling, or stagewise additive modeling, where we like to build up some additive function, some whatever basis we want, some beta basis. And we're just going to do it one at a time and optimize only locally at each step. So the punchline is, I've made enough connections here. The punchline is is that Adaboost is what's called forward, that is we add up one time, Stagewise, additive modeling, with L as an exponential loss. So before we talked about different losses for classification, 0, 1 loss, squared loss, right? There's something called an exponential loss. Turns out that this process of adding one at a time based on the answer in the previous step, which is basically just called forward stage-wide additive modeling, if you do that in a classification context with L, our loss being the exponential loss, that is Adaboost. Now, this is not how it was originally conceived, but this is basically what Adaboost is. And this is probably the best way to understand what Adaboost is. It took 5 years to figure this out, but this seems to be basically what it's doing. So that's Adaboost. It's really the basic form. The generalization of this whole boosting thing, and basically is, can we do this? Can we do, for, let's say, regression? And the answer for regression is basically yes. And I'm not going to go forward the whole algorithm. But to do this kind of forward stage-wise modeling, or an Adaboost-like thing for a regression, if the loss is the squared loss, then if you remember, our margin in the classification loss played the same role as the residual in the margin in the classification loss played the same role as the residual in the regression loss. And the punchline here is that at each step, fit new model to residuals of the previous. So let's just go back up to the Adaboost algorithm. The Adaboost algorithm reweighted the training examples. It fit the model, computed the errors, and then it upweighted the examples we got wrong. In a regression context, so you can understand that process is actually a forward stage-wise additive modeling where your loss is an exponential loss. If you do that, this is basically an approximation of that algorithm. What if I have a different loss? Let's say the squared loss. I'm solving a regression problem. What would my algorithm be different? Because this isn't going to be a different algorithm because it's not the optimal thing to do if I'm looking at, if I'm not looking at classification with an exponential loss, which you get this Adaboost algorithm. If I'm looking at a regression problem with a squared loss, what do I do? Well, instead of upweighting training examples I get wrong, basically at each step, I'm going to fit my model here to the residuals of the previous model. So I'm going to fit to the residuals of the previous model, which is a similar kind of thing by forcing it to focus on the places where it did bad. If you have a big residual, our next model is going to focus on the place where those residuals were large. In the same way that the Adaboost algorithm, if we have a very poorly classified example, we're going to, in the next iteration, or next method we're going to build, is going to focus on that. And so for a squared loss in a regression context, basically in step 2a, we're going to fit our new model to the residuals of the previous and focus that, therefore, on the place we did poorly in the last example. So in the last couple minutes here, the kind of more broad question is, what if we have a loss besides an exponential loss? Or in a classification context, or a squared loss in a regression context. These losses are not robust, so the squared loss is not particularly robust, and in the same way, the exponential loss is not particularly robust. It tends to way overweight examples where we do get wrong. because it's kind of exponential. And so the kind of more broad question is, can I use a more robust loss? What if I, in regression, if I use the absolute value loss, I got what's called a quantile regression, right? Can I use a more robust loss that won't have issues? Because if you have a bunch of outliers, Adaboost or the regression version of it is actually going to have some issues, going to over-focus on those. And so one of the questions out there is, can I fit this for a more general loss or more robust loss? The reason I like either the squared error loss for regression, because at each step I'm just fitting the residuals, really easy to fit, or my eta boosting, I'm basically implicitly using an exponential loss, and all I have to do is reweight my examples. If I don't use one of those two theoretically nice losses, this is harder to do. The squared loss or exponential loss lead to simple algorithms. Let me spell algorithms here. Either fitting the residuals, or we're just reweighting our examples in a really simple way. And if you have more general losses, actually it's not that simple. The optimization problem, with forward Stagewise optimization problem, because basically what we said is that we have to solve this argmin here. This argmin, either for a squared loss in regression context or exponential loss in the Adaboost algorithm, are actually pretty simple. Either it's reweighting or it's fitting the residuals, right? So that's really nice. But if I change to an arbitrary loss here, that's actually not, that's going to be a lot harder to get. And this leads to the more general boosting algorithms called gradient boosting. So this is our solution, and it's a fairly large step up in complexity, all motivated by basically what we want to solve is this step here. Now, to solve this minimization problem, we don't have a nice, basically closed form solution like we will with exponential loss or squared error loss. And we're going to have to basically numerically approximate how to solve this problem with basically gradient descent. So in order to solve that, we're going to have to basically solve this with some kind of gradient descent. And it's kind of a big step up. I will say that just as a flavor of the analogy, if you're familiar with gradient descent, what it says, if I want to optimize an algorithm to gradient descent, we go at time step 1, 2, 3, right? At each time step, what we look at is f of x at the current time step, or let's say x at the current time step, we calculate as f at the previous time step plus, or I'm sorry, for descent, minus the gradient of f at this point, at this previous time step. That's supposed to be t minus 1. And then we take some certain step in that direction. It's called alpha t. So if you're not familiar with gradient descent, we can ignore this. But the gradient descent basically iteratively updates our estimate by just stepping in the direction of the gradient. Step, 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 right? So it updates the position at our current point is where the function, I'm sorry, we just want to x, sorry. At the current point, and then we step in. We take the previous point and we step in the direction of the gradient by some step size alpha. So it's alpha, it's the current thing, minus or plus negative alpha times something. Now, this alpha times something, if you go look back up at, say, our boosting algorithm, we have alpha times something. Or more generally, when we're talking about this forward Stagewise approach, if I can find it. Let's see if I can find it, right? What we said is we do this iterative approach, and we take our current position, and we take a step with some alpha in some direction. So you can interpret this algorithm as solving basically a functional gradient descent. It's a little beyond the scope here, but you can basically interpret this whole algorithm as a gradient descent algorithm, as a functional gradient descent algorithm. And so you can generalize it into what's called gradient boosting for any loss. This is definitely a more advanced method. I realize I've been going through this today, which is typically why it's kind of only glossed over at this level. But that's the general lay of the landscape. It's just basically adaptively refitting and up a series of weak learners. Typically what we use for classification is some really either a classification or a regression. We use just a series of weak learners, so some stumps, just some single split trees. And we kind of iteratively update and generate a series of these where the ones further down the series are trained to specifically focus on the places the previous ones did poorly on. And it turns out if you take the correct weighted average of these, either a weighted vote for classification or a weighted sum for regression, you can get quite a powerful method. So in closing here, I just want to compare this to random forest because it's often brought up after random forests. So random forests work by reducing the variance of an approach by averaging things together. They are therefore hard to overfit. It's pretty hard to overfit a random forest algorithm, but they are easy to tune. Because they're hard to overfit, there's not really that many tuning parameters you have to play around with. You kind of just set it and go. And they work by reducing the variance, by averaging independent things together. Boosting, and the kind of generalization gradient boosting. So these are both kind of what we might call ensemble methods. And they work by bringing together many different classifiers or regression methods by averaging or voting many different methods. So random forests do that by finding a bunch of independent things, averaging together that reduces the variance. They're hard to overfit, but they're easy to tune. Boosting, they're not going to be independent of each other. We're not going to get that reduction in variance that much. It's going to work by reducing the bias. And one way you can understand that is we focus it more and more on the examples we do poorly on. So the way that the ensemble is working better than the individual methods is that it's reducing the bias by ensembling them together. You can overfit them, unfortunately, because it needs some tuning. So you can overfit them. Typically, we keep the base methods really simple, as these just stumps. You have to decide how many you include, what your capital B is in this algorithm. If you choose too many, you can overfit. So they do require some tuning. If you do the tuning, they're one of the better algorithms out there, but if you're worried about that, a random forest will do quite well and won't have any tuning. So these two methods really should be in your toolkit because they are some of the kind of more advanced, modern. Both of these have been developed, I think, late 90s. Which I guess is modern, and they're quite powerful and used all over the place. Okay, so that was a nice short little overview of boosting. We didn't get all the technical details, but it gives you a sense of what they are, how they're related to some of these other things. And they're definitely more complicated than something like a random forest, but they can be powerful. And frankly, you don't actually have to know all the math. You can run the code and it works. So I'll stop there.